If you drop a solid piece of steel into a glass of water, it goes straight to the bottom. So when you look at a massive cargo ship piled high with shipping containers, how is it sitting right there on the surface? That entire vessel is made of the exact same heavy steel. The issue comes down to density. Steel is much denser than water, meaning gravity pulls it downward with great force. A Greek scientist named Archimedes figured out the physical math behind this puzzle over 2,000 years ago. He realized that to understand sinking and floating, we have to look at two opposing invisible forces, buoyancy and density. To see how a ship weighing hundreds of thousands of tons remains on the surface, we need to look past the metal and start looking at the water pushing against it. Archimedes discovered a strict rule. When an object enters a fluid, it pushes some of that fluid out of the way, and in response, the fluid pushes back up with an equal amount of force.
Think about getting into a bathtub. When you sit down, the water level rises because your body pushes the water out of its way. But that displaced water actively pushes back up against you. This upward push is buoyant force, which is why you feel lighter in the tub. Whether something sinks or floats is an unending tug-of-war between two forces. Gravity pulls down based on the object's mass, while buoyancy pushes up. In this diagram, we see why wood floats. It has low density, so the downward pull of gravity is weak enough that the upward arrow of buoyancy overcomes it. But swap that wood for a same-sized lead block and the story changes. Lead is extremely dense. Gravity pulls down so hard that the buoyant force is overpowered and the block plummets. The rule is absolute. For any object to float, its overall density must simply be less than the density of the water it pushes out of the way. Which brings us right back to our original problem. If floating requires an object to be less dense than water, how does a heavy steel ship survive? The answer is that a ship is not a solid block of metal. It is essentially a thin outer shell of steel wrapped around a massive amount of empty space and air. Looking at this cross-section of a ship's hull, averaging the heavy steel on the outside with the light trapped air on the inside drops the overall density. Because this average density is low, the hull displaces a huge volume of water, which pushes back with enough buoyant force to carry the ship. You can test this in your own kitchen sink. If you crush a piece of aluminum foil into a tight, solid ball and drop it into the water, it sinks immediately. But if you take that same piece of foil and shape it into a wide, hollow bowl, it rests easily on the surface. You haven't changed the metal, you've just trapped air inside it. Ships stay on the surface because of the vast amount of empty space they are engineered to hold, rather than the materials they are built from. So what physically happens to the balance when that internal space is compromised? We can look at the sinking of the RMS Titanic as a famous historical example of this physical failure. When the ship struck an iceberg, the impact tore small holes along the hull. This opened a pathway for the ocean to flood into the previously hollow interior. Looking at this cross-section, we see what went wrong. As heavy ocean water rushed in, it displaced the air keeping the ship afloat. With the air gone, the ship's average density skyrocketed. Gravity finally overpowered buoyancy, pulling the ship to the ocean floor. If we think back to that sinking steel bolt next to the floating cargo ship, the interaction between gravity and buoyancy is now easy to see.